Welcome everyone. So this is our 83rd live stream geometry. We have me and 4 other people here with us now. So a pretty good group. And today I'm taking a bunch of problems from another Discord channel called Geometry Discussions and Problems. So yeah, it's just another like geometry-based Discord channel, and they post a whole bunch of what they call riddles, like easy, medium, and hard. So we're doing some of the harder ones today. And so with that, I'll share my screen. And as usual, if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. We do the session every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. Can you all see it? Can you see the first problem?
Yeah.
All right. So we have a triangle ABC with circumcenter O and altitudes BE and CF. So I don't know if you remember this one, Stefan. I think this one was posted really recently.
I saw it, but didn't work on it.
Didn't work on it yet. All right. So BE, CF, and AK is the median. So let me draw the two tangents at B and C. And they should intersect at a point. And we want to let this intersect BC at K. And T lies on OA, so let's call it O, the center of the circle. And we want TK to be perpendicular to BC. So I'm going to draw ray through O and A, then draw perpendicular. And this is T, and we want to show EFTK is cyclic. Sorry, this should be T. All right, so now I'm going to make it look a little nicer. So yeah, this doesn't seem like it's probably one of the harder problems. But we will see. All right. I'm going to draw TK, BE, and CF. And I don't need to draw. Maybe I'll draw sometimes it's useful to have this point right here. We'll draw that. One second. All right. So yeah, that's not the 9-point circle, obviously, because that would pass through the midpoint and midpoint of this side and the foot of altitude. All right, so there's a couple things when we want to show something cyclic. We can try to do an angle chase. We can try to find another point that lies on that circle. Or we could try to use power of a point. So which one do we think is best? Let's see. I wonder if TF and EK. No, I don't. I would be surprised if they meet on the circle. So yeah, let's see. Where could we use power of a point from? Let's see. That was tricky. I don't know if we could use some mothity. But yeah, the problem is very simple to state. Yeah, you just let the median intersect BC at K, and then you draw perpendicular to AO. Hmm. Like there has to be like another point on this circle that is special. Maybe this point or something. Let's call it something else. We know this is the orthocenter. So yeah, it's JK a diameter, the circle. No, it's not. It almost looks like JH is parallel to AB, but obviously that's not true. Maybe we could use the power ratio lemma. So we know E and F lie on this circle. And E and F also lie on this circle. So yeah, maybe the power ratio lemma would work. Let's see. So KB times KC, that's the power of K with respect to this circle. And then this one, I don't know if there's a good way to do it. could try drawing these. We know TK is parallel to AH. I don't think that's a parallelogram. Obviously, HM and D are collinear. So IO is parallel to HD. Yeah, I just don't know how much this stuff helps.
Okay. I have seen a problem before, which looks useful here. That is that AM, TK, and EF concur.
Okay. AM, TK, and EF concur.
Yes.
Interesting.
Don't know the proof of that, but doesn't look too hard.
Okay.
And that sets up nice for maybe powerful point.
Yeah. Yeah, then we just need to show TJ times JK is EJ times JF. So AO and AH are isogonal. I'm thinking how we use power of a point.
I think A, T, K, and a Humpty point should lie on a circle.
Okay. So this is the Humpty point right here.
Yes.
And ATLK is cyclic, is what you're saying. Interesting. Let me move this out of the way. I'm going to hide these circles for now. And yeah, EF, LH, and BC meet at a point. But yeah, I'm not going to draw that point just yet. Actually, maybe it's worth having this circle because we have the Humpty point.
After we prove that J exists, and then it is equivalent that EFTK is cyclic, that is equivalent to showing that ATLK is cyclic, just by powerful point.
Ah. Because, yeah, then we would have TJ times JK is AJ times JL, which is EJ times JF. So Timo, did you prove that this was cyclic, or you just saw that, or you saw that it was equivalent to the problem?
I only saw that this equivalent.
Okay. All right. I wonder if like T is the midpoint of RKL. See if that's true or not. Yeah, it looks true. So basically it looks like KT is the angle bisector of AKL. And maybe that's just projective geometry, because let's see. So we could try.
Yeah, we can prove that by projective geometry, since ME and MF are tangents to circle AF.
Okay.
Then ALJM is harmonic.
Oh, since these are tangents. Okay.
Yeah. And then since the angle MKJ is 90, we get like an Apollonius circle.
Okay. So AJLM is harmonic. And I mean, once we know that's harmonic, then that means KAKL, KJ, KL, KM is harmonic. So yeah, it has to be an angle bisector, right?
Because MKJ is 90, that is why it needs to be.
Yeah, exactly. All right. Interesting. So did we, okay, so we know T, yeah, we know we have an angle bisector here. Is that enough to show that this is cyclic?
We should prove that EF, AM, and TK concur. I think that is really important.
Yeah. All right. I'm going to hide this circle for now just because it's big. But yeah, that's ultimately what we want to show. Oh, wait a sec. Wait, so, yeah. But yeah, once we know that this is an angle bisector, does that solve the problem? So if we could show that TA equals TL, that would solve the problem.
Okay, I proved that AM, EF, and TK concur.
Okay.
Basically, we let AM and EF intersect at J.
Okay.
Then we take K such that JK is perpendicular to BC, just redefining the points.
Yeah.
And then we want to show that AK bisects segment EF. That would mean that mean that AK is the symmedian.
Okay.
So we take the midpoint of EF.
Oh, sorry. Okay, I got confused a little bit. So, yeah, so T and K can both be defined like this, but
yeah, T is not important for this part, but
okay.
yeah. Then since M is midpoint of BC and N is midpoint of EF, it is well known that MN is perpendicular to EF.
Wait, sorry, say that one more time. So M is the midpoint of BC.
And N is midpoint of EF.
We wanted to prove that N is the midpoint of EF, right?
We define N as the midpoint.
Oh, okay. Okay.
Then MN is perpendicular to
EF.
EF, yeah.
Okay.
And so that means that KMJN is cyclic, since MKJ is also 90.
Okay.
Then we have that angle ANJ. I mean, we have angle ANJ that is equal to AMB because M and N are corresponding points in similar triangles, AF and BBC. But AMB is equal to KN 180 minus KNJ.
Okay.
So
Which shows that
basically
AN and K are collinear.
Yeah.
Interesting. Okay. So I'm going to write this up so far. So I'll call this K prime and this, yeah, I'll just leave that as T for now. So let AM intersect EF at J. And let K prime be the foot of the altitude from J to BC. And then we want to show that AK is a symmedian. Check the chat. Oh, to the Discord for that I'm taking these problems from. I could send it right now. Hold on just 1 second. Sorry. Give me just a second. It's this one. So no, not that one. Sorry. This one. But yeah, don't look at the answers, but here's the server. Right. All right, so I will copy it into the chat. Okay, so then we have, you're welcome. So since M is the midpoint of BC, so let N be the midpoint of EF. And then angle MNE is equal to angle M, or angle MNJ is equal to angle M. So when we know this is 90 because BFEC is cyclic, so I'll just write that quickly. So BFEC is cyclic, and that implies angle MNJ equals 90, and which is equal to angle MK prime J. And that means that MK prime NJ is cyclic. And once we know that, it's not hard to show that A, N, and K prime are collinear, like you said from an angle chase, because we have angle A, NJ is equal to angle A, MB. Which is 180 minus angle K prime NF. And that means that A, N, and K prime are collinear. And that means that K prime equals K. Okay, so we can draw that. And that's how we know that these three are concurrent. All right.
I think I have a proof for the cyclic quadrilateral.
Okay.
And I intersect the tangent line to ABC at A with BC.
Okay. This is interesting.
And now by properties of the Humpty point, KA is equal to KL.
Okay. I'm gonna rename it. Sorry, I'm gonna rename this I don't know, R. So RA is equal to RL.
Yes.
All right.
And now we know that BC is the exterior angle bisector of AK prime L. I think we proved this before.
Yes. Yeah, we proved it using harmonics and stuff like that.
Yeah, exactly. And this means that A, R, K prime, and L must be cyclic.
Oh, because okay, so A, R, K prime L is cyclic because RA is equal to RL, and this is, yeah, an angle bisector.
Yeah. And now we also get that T lie on this circle because angle RIT is equal to 90 degrees and angle TKR is also equal to 90 degrees.
Ah, very cool. All right. So let the tangent to ABC at A meet BC at R. And so first, ME and MF are tangent to the circle. That's well known. So that implies that this is harmonic, and then which implies angle bisector. So ME and MF are tangent to AF, the circle AFE. That's well known. And that means that A, L, J, and M are harmonic. And that means that KJ bisects angle AKL. Since angle JKM equals 90. And then, so RA is equal to RL, that's well known. That means that, so I've seen this before, I think I might have forgotten the proof of it, but that means ARK L is cyclic. And then angle TAR equals angle TKR equals 90. That means that TARKL is cyclic. And then we could use power of a point, because now we know that EJ times JF equals AJ times JL. So is equal to, sorry, I'll fix that. And AJ times JL is TJ times JK. That means that EFTK is cyclic. All right, this is a fun one. So yeah, we use this fact that RA equals RL. I'm just trying to remember. Basically, that means that the Humpty point lies on the circle centered at R with radius RA.
Yeah, this is the Apollonius circle of ABC through A. And to get this, you must do an angle chase.
Okay. All right. Okay. So yeah, we could go back to the proof of that later, but basically, sorry, we're saying that L lies on this circle. And to prove that,
I think it follows from another property that when you reflect L over BC, that will be like on the C medium. Like
okay.
the circle, the intersection of C medium with the circumcircle. And that I don't know if it can be like angle chase or something.
Okay. Yes, because like the Apollonius circle goes through the intersection point of the A angle bisector with BC, and then you can prove with, I think, projective geometry that also the intersection of the AC median with the circumcircle of ABC lies on the circle, this point K. And yeah, and then you use the property that L is the reflection of this point of X over BC, and then you got it.
Okay. Interesting. All right, very cool. So yeah, thanks for that very nice solution. That was a fun one. All right, so here's the next problem. So we have a triangle ABC with circumcenter O. Stefan, did you see this one?
I think no. I think no.
Okay, that's good. So this is O. And again, we draw the tangents at B and C. So I'm gonna make it look a little better. And then we draw the circle with center P. So something like this. And we see where it meets the internal bisector of BAC. So all right. So I'm just going to do it like this. So this is P and this is S. And then OS meets BC at D. And E and F are the projections of S onto AC and AB. So S is on the angle bisector. So that means we would have like a cyclic quadrilateral. I'll rename this M. And this will be E and F. And then DF intersects AS at X. So we want to see where DF and DE intersect the angle bisector. Okay. So this is a tricky diagram. Yeah. Let me make a few things look nicer first. Yeah, there's a lot going on here. So we have PB and PC for the tangents. And then we drop a perpendicular from S to both those sides. And we see where DE and DF intersect that angle bisector. So this is a tricky diagram. Let me see if there's any way I can make it better. Okay, so it could be that they both intersect it like inside of the circle. That's what I was hoping for ideally. So yeah, maybe something like this. That looks all right.
Looks like BY and CX are just perpendicular to AS.
Oh, really? Okay.
Yeah.
So hold on one second. Let me just draw them first. So this is X and that's Y. We want to make H point Y. Okay. Is that something you noticed from the diagram, or you can prove it?
If we can prove it, then we are done. I just noticed it.
Okay. So yeah, I guess we can then hide a lot of the diagram. Like we don't really need, because once we prove it for one part, then we don't really need the other part. So we could just make the diagram look like this for now. Oops. So we want to show XB is perpendicular to AB.
No, XC is perpendicular to AS.
Oh, sorry. XC is perpendicular to AS. Yeah, it seems kind of silly, like that. Like they would make the problem look harder than it really is just by like them both being perpendicular. But yeah. So yeah, I don't know if it's worth redefining things. Like we could take the perpendicular from C to AM and then try to show these are collinear. There's a dog barking outside my apartment. I don't know if you guys hear it. Or not my apartment, my parents' house. Um, I'll draw this in. So yeah, it's not too often that I see like you intersect this circle with the angle bisector. It's a little straighter. So yeah, I don't know if it's worth drawing the foot of the altitude from A, and then we could try to show that we have a cyclic quadrilateral. So yeah, I don't think F lies on that circle. So yeah, we could have a diagram like this. to be the foot of the altitude. So yeah, we could draw this circle and let it intersect AM at x prime, and then we can try to show that these are collinear. Hide it. Oops. One sec, I'll be right back. All right, thanks for waiting. Looks like Simon left. Okay. All right. So yeah, we have this point S. We have two right angles here.
Maybe it's a good idea to intersect BC with the tangent line at S to the circumcircle of BSC.
Okay.
And
All right.
and now if we draw in the tangent of H to the circle, the second tangent,
Okay.
not HS.
Um, Oh, whoops. Sorry, it's off the screen. Hey, Simon, thanks for rejoining. Okay, so this is the second tangent. There we go.
Yeah, and now O, S, D, and I are collinear.
Okay. Oh yeah, it's all right, Simon. I've had some issues with my connection too. Okay, so those are all collinear. Basically, that's the same as saying that O lies on the polar of H, which is the same as saying that H lies on the polar of O, but that's clear because angle OP.
Yes.
Yeah. So those are tangents. Interesting. Yeah, it does seem like that would probably be helpful in this problem.
We just want to show that ASC, triangle ASC and AFX are similar.
Oh, really?
Yeah.
Interesting.
After that, angle chase can finish, I think.
ASC and AFX. So we want to show that there's a spiral similarity. Yeah, I see what you're saying. Yeah, that follows, from a spiral similarity. And yeah, we know one of the angles is equal, so. So yeah, can we show that this angle here, ACS, is equal to AXF? Yeah. So yeah, SBIC is harmonic. And so the cross ratio OSDI is harmonic, and so is HBDC. And we have that angle OGB as a right angle. So BC is the bisector of angle SGI. And similarly, I think IS, let me think about that. So yeah, Simon, this is actually that problem that we did. Remember, BC is the bisector of SGI. That was that problem you asked me about.
I don't really remember it right now.
Oh, it's all right. It's fine.
This was a problem in a German contest, I think 2 years ago or something like that.
Oh, really?
Yes.
Interesting. So actually, I just found a second proof of the thing that I told Simon. But yeah, sorry. But so on the one hand, we know BC bisects angle SGI because we know that OSD and I are in harmonic conjugation. And so since this is a right angle, then this has to be an angle bisector. So that's the first proof. The second proof, you can use symmedians because in triangle IBC, we know that IO is a symmedian. And in triangle SBC, we know that SD is a symmedian. And if you do some angle chasing, then that means this is an angle bisector.
Oh, now I know what you're probably doing.
Yeah. So I just found another proof of that problem that we did, but yeah. Okay.
I also think that HF is perpendicular to AS, but I'm not sure why.
That's interesting. So that would mean HJGM is cyclic.
Now we should probably add back in the points we raised at the start.
Oh, you think it'll be helpful?
Yeah, because we will have 3 concurrent lines.
Okay.
At least E.
Okay.
Don't know if others will help.
What would E do?
You see E, F, and H should be collinear then.
Oh. We'll just make O a little bit higher up. So basically, yeah, can we show that EF, BC, and the tangent at S concur? That's, yeah. Is this an angle bisector here? Let me check. No, it's not. So yeah, maybe it's worth drawing this circle. Yeah. Oops. Sorry. I want to make it like just the right size, but it's hard. I think that's fine. So yeah, we want to show that these three concur. We know that BFEC is cyclic, so I wonder if, well, no, actually we don't know that. That's not true. You know, we know that this is cyclic. I'm wondering if there's some way to use the radical axis theorem. Now, what is the radical axis of these two circles? Like, is HS the radical axis? It would have to be if the problem is true. So basically that means
HS, the fact that HS is tangent, that is equivalent to showing that BE, CF, and AD concur.
BE, CF, and AD.
AD, yeah.
Oh, okay.
Because we basically want to prove that HBDC is harmonic.
Okay. So is HS tangent to this circle? I don't think it is, but I don't know. Let's see. No, I don't think HS is tangent to that circle, right?
No, it can't be tangent because AP, no, because the midpoint of the circumcircle of AFSE lies on AS and P does not.
Okay. Okay, so we want to show, I'm going to hide, well, no, I don't want to hide it, but we want to show BE, CF, and AB concur. That's interesting. So yeah, maybe Chuba's theorem could help with that. Because if we know that, then that would mean that HBDC is harmonic. And yeah, so those are the tangents. So yeah, we don't yet know that this point is there, but if it was, we'd have a cyclic quadrilateral here. So yeah, we have to use something about how S is defined.
D is the orthocenter of HOP.
Oh, really? So we know HD is perpendicular to OP.
We know that if we define H as the like HS is tangent.
Yeah. It's not too hard to show D is the orthocenter of HOP, right? Because
If we know that the HS is tangent.
If we know that HS is tangent. So so I guess we're kind of defining H this way. So we call it like H prime, or well, we could just leave it as H because it's not in the question. We want to show that HS is tangent. Okay, so yeah, so D is the orthocenter of HOP. Oh, if we know HS is tangent. Yeah. All right, we could try this for like another 10 minutes, maybe 15 more minutes before we move on to the next one. Looks like a good problem. Yeah, the trick is using that that OS and B are collinear. We draw this. Try some. Okay. Yeah, there's a lot of interesting stuff in this configuration. Yeah, it's weird. Yeah. So SBIC is harmonic, or we want to show it's harmonic. Hmm.
Bx should bisect HF. That would after we prove that HBDC is harmonic.
Okay.
That would be after that. This would be equivalent to the problem.
Showing that BX bisects HF.
Yeah, just by projection through X onto EF.
Okay. Yeah, that makes sense. Let me make X farther away from M. I like that.
I have two more cyclic quadrilaterals, but I'm not sure if they are that helpful. So the first one is if you draw in the circumcircle of K, S, and A.
Okay.
And now you intersect HM with the circumcircle of ABC.
HM.
Yes, exactly.
These concur. Okay.
And also you have that A, G, N, and H as cyclic.
AGM and
No, never mind. Not G. That was the wrong point. I meant the intersection of the angle bisector with BC instead of G.
okay. So AQM or AQH and N.
Yeah.
Interesting. So this point N has a lot of circles going through it.
And if you take the first of these two circles, then and bisect AO with PS, this point should also lie on the circle.
AO with PS. Okay.
But I'm not very sure if this is helpful in any way.
Yeah, it's interesting. Let's see. Let's check.
And HJSN should also be cyclic.
NHJS. Did you say NHJS?
Yes, but probably I made a mistake.
Sorry. Well, because this looks like a right angle, but
Yeah, and never mind. I think I got something wrong.
that's all right.
Maybe it's useful just to notice that SG and SD are isogonal in BSC.
BSC, SG, and SP are isogonal.
SD. It is just like
SD.
the
Oh,
median
yeah.
and C-median, but
Yeah.
we can kind of think of it like that rather than intersection of S, so it looks like a bit simpler.
Yeah, SD and SG are isogonal. Yeah. Do you mind if I hide some of these for now? So ANQH. To remember that. Yeah, so basically we don't really need 0.0 is what you're saying. Like we could just draw this circle right here. Then if G is the midpoint of BC, but yeah, we'd still, yeah, we'd want to use that fact. Yeah, this looks a little tricky. Do you want to move on to the next problem and maybe come back to this later? What do you guys think?
Maybe a few more minutes on this.
Okay. All right. So yeah, I think SBI is similar to SGC, right? Yeah, that's just an easy angle chase. It's tricky.
HR should be perpendicular to AO, I think.
Okay. That's an interesting observation. So we knew that I think AR what was our, I forgot. I think it was this ARSKN was cyclic. So that's perpendicular. We want to show CX is perpendicular to AS. So yeah, obviously that means HROG would be cyclic. So yeah, we want to show CX is parallel to EF. I don't know if we could try to show angle XCH is EHC or something like that. Yeah, we have a lot of right angles here. So yeah, we have a lot of cyclic quads. But yeah, none of the thing is none of the cyclic quads pass through point X. It's the only thing. All right. I think I'm gonna move on to the next problem. But yeah, we can come back to this later. Looks like a hard one. So here's the next one.
Could you just go back? I think I have some progress.
Oh, really? Okay.
Yeah. Okay, so about proving that HBDC is harmonic.
Okay.
We know that SD is median of BSC.
Yes.
So we have that BD over DC that is equal to SB squared over SC squared. That is a
Okay.
well-known theorem.
Yeah.
And we want to show that BD over DC is equal to BF over CE. So by Chow, we could show the concurrence. And right now I'm doing a bit of algebra with Pythagorean theorem. And I think I have some stuff that cancels. I will just do it for a minute and see what expression I will get. It
Okay.
isn't bad at all.
Okay. Yeah, I see what you're doing. You're trying to show by Cheva that these concur, and we know that BD over DC is SB squared over SC squared. You just want to show that's BF over CE. Interesting. And then that would show that HS is tangent, right?
Yeah.
What is the thing you want to prove? Can you repeat?
So Stefan basically has a proof that HS is tangent to the circle. So if we so he defined H a little differently. He said let EF intersect BC at H, and S is just intersection of AM with this circle. And he has a proof that HS is tangent to the circle, or he's trying to prove it.
Okay, I got to this expression. We want to show that SE squared, or like the more symmetrically SE times SF, but it's the same. SE squared is BF times CE. That is what we want to show.
Okay.
I don't know how easy or hard that is right now.
Interesting. So yeah, let's think about that. So that means if BF or CE gets close to 0, then SF and SE. Let's see. Well, like that almost doesn't look, because like here, like BF is like really, really small. But SF and SE, you see what I mean? But I don't know, maybe it's just a bad diagram. Like,
could you could just type it in GeoGebra to see if it is correct. I think I'm getting the same numbers, so
yeah, no, actually I think you're probably right. This is probably just it's probably just hard to tell. So but yeah, I'm pretty sure what you're saying is true. Like your argument makes sense. So like so yeah, is this times this equal to that squared? Let me use the calculator.
oh, this is actually just equivalent to showing that SBF and the SCI are, SBF and the SCE are similar.
Yeah. And
I don't know how we didn't see that before.
Oh, and is that just an angle chase? Because angle SBC, that's equal to half of SPC. Yeah, that might just be an angle chase. So SBC is half of SPC. So oops. Oh no, we would want to show, yeah, this angle. Okay, so yeah, we want to show that these two add up to 90. Yeah, okay, no, I can prove they're similar. Yeah, that's just an angle chase. Because we want to show angle FBS plus angle SCE is 90. But if you add up those two, that's the same as taking angle B plus angle C and then subtracting SBC and subtracting SCB. But it's easy to show. You can angle chase that pretty easily. So, okay. So yeah, basically that proves that HS is tangent to the circle, right?
Yeah.
And then we know that these are collinear, and we know D is the orthocenter of HPO. All right. Now let's see if let's spend like 5 more minutes on this, see if we could use that. But yeah, I like that idea. So yeah, once we show BE, CF, and AD concur by Cheba, and that means HBDC is harmonic, and that means that, yeah, HS is tangent. Because yeah, OB and OC are tangent, so that has to be.
I think now we could like project HBDC from F to XC.
Oh, HBDC through F to XC. Okay.
Then we want to show that AF, wait. Yeah. Then we intersect AB and CX and hopefully get something useful.
Okay. I mean, basically, we just want to show. Wait, is that trivial? So wait, HBDC is harmonic. We're going to project through F onto XC. Then we get TXC, and we want to show it's the point of infinity, but like X, since this is an angle bisector, is it just obvious? Yeah, maybe that solves the problem. I think it might.
No.
No.
We have to show that. Yeah, I mean, this thing with midpoint, we don't even have to project to let's say it is equivalent. Yeah. You'll like just have a symmetry about the angle bisectors, T and C. T and C are symmetric about the angle bisector.
Yeah. So if we project through F, oh, so basically this is just like, this is another way to show that these are harmonic, right? Like instead of using Chev and doing all that, what we could do is we could have, oh no, I feel like we're going in circles. Yeah, because we don't know that X is the midpoint of CT. Yeah, I mean, it's equivalent to showing like L is the midpoint of HF, for example. Okay. Okay, so all right. So I think I'm going to move on to the next one and come back later, unless you guys end up finding something like really quickly. But yeah, it's a tricky problem. So we have, sorry, triangle ABC with circumcenter O and orthocenter H.